So now that we know, this is chapter 19 lecture still, we're looking at Gibbs free energy. And so the first thing we're going to discuss is if we're just looking at a chemical reaction, can we determine if its delta G is positive or negative? So this is the equation we use for delta G is equal to delta H minus T delta S. And again, it's on your formula sheet. Now the one thing I do want you to write in are little degree sign. Again, the degree sign means we're at standard conditions at 25 degrees Celsius, 1 atmosphere. So you're going to see those degree signs in most of the problems that I'm going to give you. So the goal here is to get delta G to be negative. Okay, that is the goal. So I have 4 different scenarios here. So if you want to do 1 through 4, just so you can see where this all goes. And I'm essentially looking at what is the delta H sign, what is the delta S sign, and then what is the delta G going to be. So again, using this equation, we want delta G to be negative. So the first scenario is, what if delta H is negative and the delta S is positive? Well, if the delta S is positive, that means this quantity is negative, this quantity is negative. So it's going to be always spontaneous, and there is going to be no exceptions to this, no exceptions to this. All right, so let's look at scenario number 2 a little bit more extensively. So delta H is negative, okay? Now that means it is exothermic, so please note that that means it is exothermic. And we have talked about before that exothermics are usually favored in chemistry. But what if the delta S is negative? Okay, so that means entropy is going down. Okay, entropy is going down. So if you want to use arrows along with these, you could do that as well. So it's becoming more ordered. Okay, so it is spontaneous at what we call low temperatures. Well, why is that? Well, if we look at the delta H being negative, okay, and I am saying the delta S is going to be negative as well. Okay, so that's going to make that part of the equation positive. Okay, so the only way this is going to stay as a negative, because again, the goal is to get delta G to be negative, is this exothermic portion needs to be pretty big, and so this has to be a low temperature when I multiply this to keep it below this threshold of negative. Okay, because this is going to be a positive part of the equation. So spontaneous at what we call low temperatures, and you need to include that when you are describing whether or not it's spontaneous or not. So what if we have endos? Okay, well, we know endos work, okay, but what if we have an increase in chaos? It will be spontaneous at high temperatures, okay? So let's look at scenario 3. So my delta H is positive, and my delta S is positive. Okay, so that's going to keep this part of the equation negative. So what I want is this to be large. I want this to be a really big magnitude-wise. So I'm going to multiply it by a high temperature, so it's going to be greater than this positive delta H to make that delta G. Okay, now there's no magical temperature for low or high that I can give you. It depends upon the math that you are given. Now, scenario 4, if it is endothermic and it's becoming more ordered, it will never happen. Okay, no matter how much you want it to happen, it's not going to happen. All right. So those are the rules for delta G, depending upon if it's exo or endo, and if you have an increase and decrease in entropy. So let's look at these 2 examples here. So I have nitrogen plus hydrogen makes ammonia, our Haber process. I have 4 moles on the left and I have 2 moles on the right, okay? So I am predicting that the S is decreasing, okay? Because of the fact that it's becoming more ordered. I also have 4 things going to 2 things. It's kind of a combination reaction. In the sense of I only have 1 molecule here, I have 2 molecules here. So that means my delta S is going to be negative. My delta S is going to be negative. And it's telling me it's an exothermic process, So let's see. So my delta H is negative, minus T, and a negative S, So the S is going to, that negative S is going to make that portion positive. okay? So this is going to be spontaneous only at low temperatures, because I need this part of the equation to be relatively small so that I could have my delta G be negative. All right, so why don't you try the next one, and then I will come back and show you the answer. So the second equation is going from 4 things to 1 thing, so you have a decrease in entropy, so that's going to be negative. But when you put it into the equation, it's going to then become positive. And since this is an endothermic, the delta H is positive here. I have a positive here, a positive here. This will never, ever be spontaneous. So again, if it's endothermic and a decrease, it will never happen. Okay, so now we're going to talk about some of the math that we're going to be doing. And we're going to start with S, entropy. So you're going to need this table that I have provided for you, because we're going to be referring to those numbers. So we have something called the third law of thermodynamics, which is talking about entropy still. And it is the entropy of a perfect crystal at 0 degrees Kelvin is 0, okay? So what that means is entropy, okay, and a perfect crystal just means solid, just means a solid, and this is absolute 0. What that means is everything has chaos. Everything has entropy. So this table that I have given you, okay, you will see that it has 3 columns, delta H, S, and delta G, okay? Now the S is what we're focusing on now. We did delta H before, and we will talk about delta G a little bit later, okay? So focus on S. Realize that when you look down this column, you're going to see everything has a number associated with it. Now some of them are positive, some of them are negative, but you have a number for everything. In comparison, if you look at delta H, you will see that some of them have zeros associated with it, and that's because they are in the elemental form, and we talked about that before. But everything has chaos, everything has entropy unless you're at absolute 0, all right? So like before, when we're looking at a chemical reaction, if we have the same amount of moles on both sides, we have to do some math. The math is always going to be products minus reactants. So again, little n here in this equation is number of moles. And you will, again, the degree sign means at standard temperature, 25 degrees Celsius, 1 atmosphere. And this table is based off of 25 degrees Celsius, okay? So that's going to be why we use those tables, okay? And please be sure you write down always have S, okay? It's never 0 unless you're at absolute 0, okay? So standard entropies, everything has entropy. Gases have more than solids or liquids. So you could actually look at this table and you can see things at different states depending upon I had to pause there for a second. If you go to the second group of chemicals over here on the right, find water is a gas, water is a liquid, water is a gas, water is a liquid. And you will see the number for water as a gas is 0.1887, and for liquid water is 0.0699. So again, that points out that you will have a difference of entropy depending upon the states of matter. Liquids are always going to have a lower entropy than gases. Entropy increases with an increase in molar mass. I'm going to talk about an example here in a second. And increases with the increased number of atoms. So for example, if I am comparing carbon monoxide to carbon dioxide compared to carbon dioxide. Both of them are gases, so that we can't look at, okay? I have 2 atoms in this formula, and I have 3 atoms in this formula, okay? So if I have an increase in number of atoms, okay, this is a more complex molecule. If you have a more complex molecule, that's going to have more entropy. You're going to have a higher S in comparison, okay? So sometimes if you have the same number of moles, you have to look at the actual molecule itself, and the more you have, the higher or more complex it's going to be. Same thing goes for molar mass. So again, if you have more mass, you have more chaos that can ensue. So in terms of the calculations, you're going to be given the reactants and the products, and you're going to have to take the balanced chemical equation and calculate what the delta S happens to be. So these are numbers directly from that table. Sometimes I'm going to give you the table, sometimes I'm just going to give you the numbers. So why don't you try that in your calculator, and I will come back and show you the answer. So the number you should have ended up with was negative 146. Now, a couple comments to make about this. I'm not going to focus on the math part. Is first off, the unit is in joules per Kelvin, joules per Kelvin. You will see that on the table it's per mole. It's per mole because, again, you're multiplying by mole. Please note that this table, it has everything in kilojoules. So just keep that in mind. I like things, a lot of other tables do S in joules, so that's why I'm using this, but please don't get confused. I will show you why kilojoules is more helpful. So this is in joules per Kelvin, because again, remember, entropy is heat over temperature, heat over temperature. This number is negative, so that means it is decreasing in entropy. Does that make sense? Look at the balanced chemical equation. Well, how many moles of gas do you have on the left? There are 3. How many moles of gas do you have on the right? Is 2. So you would have predicted without doing any math that the entropy was decreasing based on just looking at the balanced chemical equation. So what this does is show you the math side of that calculate, of finding if entropy is increasing or decreasing.